So deterministic solution. So yeah. More precisely, we have this rendezvous problem definition and two robot or two mobile agent are located in different location, and also even those two robots can be activated in different time. So, and we specify modeling related to unknown anonymous event in the next slide. So those robots and those old mobile agents cannot rely on global knowledge, and we must follow a deterministic sequence to guarantee the mean. So of course that we want efficient solution. So ideally we want to a polynomial time solution. So when we talk about the solution, we start counting the running time from the activation of the second robot. So there are a lot of applications in addition to theoretical elegance of those problems. There are a lot of applications related to network exploration, distributed system, and autonomous robotics. So, yeah. So, more precisely, we can define this environment as an undirected graph topology, and a set unknown to all robots. So, and also vertices in this graph are undistinguishable. So, moreover, exits are numbers, as was already shown in this graph. So, and also beware that there are no consistent assumption on those numbers or on this exit or port numbers. So, for example, on the top edge, the left vertex associated with port number 1, and the right one associated with port number 2. So, there are no consistent assumption. And moreover, in this challenging problem, we also assume that there are no typos allowed. So that means that the robot cannot make any marks on the vertices they visited. So that makes the problem more challenging. So robot meet when they are in the exactly same vertex at the same time. We use a synchronized model. So that means that in each individual step, the robot either stay put or move according to the guidance or according to the instruction. So what's the instruction? There are different models. So one is a memoryless model. So you are not allowed to use any memory. So in addition to this original instruction, which is a sequence. So each robot get a sequence at the beginning. So, and in each step, if the sequence element is 0, then robot just simply stay in place. Otherwise, the robot just take exit number to move. So this is an example. So we have a sequence 3202, and then robot stay on the left top, and then we from here, because the first element in the sequence is 3, then we use the number 3 to move. And then when robot arrive to another vertex, and then the second element in this sequence is 2, then robot just follow this instruction, use port number 2 to move. And similarly, the third element in this given sequence is 0, just stay put, stay in the place. So, and then the next element in the sequence is 2, and then just use port number 2 to move. So, yeah, this is basically how instruction works. And another model called a backtracking model. So when a robot enters into vertex, it learns the number of edges used to enter to the current vertex. So, for example, in this case, when robot enter into this new vertex, robot learn that the entry number is 1, with this entry enter into the current vertex. So, and this example, so this information may use properly because now the robot get extra information, and then this extra information may significantly change the action. So now since we have extra information, at least from those extra information, backtracking is possible because the robot learn the number to get into this current new vertex. So those are very useful property, very useful information can be used in the later stage to design the efficient instruction. So some parameters should be introduced. So we have this size n, size of environment is size of graph, and we have the length of smaller label, and we also have this tau difference in activation time. We already mentioned that two robots may be activated at different time. So and we have this d maximum degree of the graph, and we illustrate the major result for the rendezvous problem. So for the rendezvous problem, so we, as mentioned before, we are interested in polynomial time solution, and the first very important significant work done by Deterministic and other authors. They show a very elegant approach with polynomial time. However, this result depends on the parameter tau, which is the difference of activation time between two robots. So, and then of course, obviously, natural question will be whether we can design one independent of which this parameter tau, and later Kowalski and Marino they answer this open problem and give a solution which alter parameter tau, not depend on parameter tau. That's very significant. However, their model also must be used the backtracking information. So I must use a backtracking model. So and then later, Taisama and Duke, they improve this result. So further reduce the time complexity, and finally I improve the result further. So especially for the rendezvous problem with backtracking in backtracking model. So, yeah. So if two robots, it's well known that if two robots are identical, that means there are no distinct label, and then there are no deterministic solution. So it's impossible. There are no solution possible. So you can easily think about the scenario in a ring topology. So there are no distinct labels, no distinction on those two robots. So to break those symmetry, the robot must assign distinct label. So I1 and I2. So in this talk, we assume that the label are 0 and 1, because for longer label we can easily adopt our approach, just the multiple factor of the length, the shortest label length. So we mentioned previously in the literature review. So this also motivated to study universal traversal sequence. So a sequence tau is a universal traversal sequence for graph of size n, if for every negative graph of size at most n. So no matter how you labeling and what's the starting point in this graph, the walk defined by this sequence tau will cover entire graph. So this sequence defined universal traversal sequence. So in the literature, that Alan Lunas and others already show that a random sequence of lines big O of D square and Q log n is with high probability of universal traversal sequence for D regular graph of size n, because D regular graph is the most challenging scenario because all the vertices are not distinguishable. So, and of course, it's not for regular graph, and the problem can be solved. I mean, based on partition and yeah. But the most challenging part, most challenging scenario is for D regular graphs. So, if you can solve D regular graph, you can also solve one not regular graph. So, however, the downside is at this moment there are no efficient construction for this universal traversal sequence. So there are no efficient construction. So as mentioned before, we are seeking for polynomial time solution. So a natural solution will be robot 0 stay put, and robot 1 just simply execute this universal traversal sequence. So U1, U2 based on this standard doubling technology. So beware that UN is a universal traversal sequence for graph of size n. So the problem is that robot 0 may be activated when robot 1 is executing large block UK. So the K may be much larger than the graph size n. So that's the case. So maybe when the robot 1 already started the block UK and robot 0 is activated. So, and of course, as mentioned that we don't want exponential time solution, we want polynomial time solution. So this also motivated to study strongly universal traversal sequence. So which is a infinite sequence tau, and for graph which cover time Pn, the most important property for this strongly universal traversal sequence is that any contiguous subsequence which covering time Pn is a universal traversal sequence. This is a much stronger property than the original universal traversal sequence. So now it's any contiguous subsequence which length Pn will be a universal traversal sequence. So no matter when the robot activated, so you always have this property. So if the graph size is n, you always can use Pn to guarantee the exploration of the whole graph. So, and if the graph size is n prime, you can always use Pn prime to guarantee the one of the robot, or the robot will use this Pn prime to explore the whole graph. So that's the most important property, and also this is a very nice, elegant property for the design in the future, in the later stage. So, however, the main open problem is that do strongly universal traversal sequence exists. So that's the major open problem. So and if we having such a sequence, and the solution of the rendezvous problem can be easily solved. So if we have this problem, we not necessarily have to have this strongly universal exploration. So we do have this a universal traversal sequence, and it is represented by U, capital U, and a robot which label either 0 and 1 will follow this instruction. The instruction defined as follow. So you can easily see that we have, each time we use the standard doubling technique. So U1, U1 and U2, U2 and U4, U4 and U2K and U2K. So, and UN is universal traversal sequence for graph of size n. So we also have this data function. So the parameter k, so dk for a given sequence is the original sequence by interleaving zeros between the element in the original sequence. So that's the function dk. So having those instructions, we can guarantee that at the end the two robots will eventually meet. So now we will give an intuition about why and how those robots can eventually meet. So based on this instruction. So let's look at the specific block. So we see block K, the case block of robot 1. So the in this specific block that will run U to power twice and then stay for 2 times U to power 2k step, because that's due to the B function. So we will interleaving zeros. So because now the parameter k is U to power k. So and stay put for U to k steps between any 2 steps above, because that's the definition, that's according to definition about this D function. So interleaving zeros, number of zeros specified by this parameter U to k. So and we can show that the true robot can meet after we go through UN to 4 steps, where n is the size of the environment. So this is just based on this very it's based on this D function. I mean, based on not smart interleaving those zeros. If we can analyze or we design carefully, smartly interleaving those idle period, we can get a better solution. So we can guarantee this correct improvement. So and look at explicitly on this instruction. Look at this specific block for the robot. So because we can easily see that this case block can be easily divided into 4 sub blocks. So either start from this regular move based on this sequence, based on this instruction, which is a sequence, or stay in the place. So which is 0. 0 means stay in the place. So if L is, if the label is 1, then the robot will in the D block the instruction will be like this. And otherwise, if the label is 0, and then the K block will be like this. The start from the first sub block, which is 0, which is stay in the place. So 2 consecutive sub blocks. So and then start running the regular instruction, regular sequence to move. So the property is that we want to guarantee that always exists a period that one robot run this one subsequent sub block Wn, and another robot just keep stationary or just stay in the place. So that's because the Wn contains one universal traversal sequence. So that's a guarantee that eventually this one will meet the one stay in the place. So however, the remaining part we must be dealing with the activation time. So and we can easily see that we just assume that if the second robot active at when the first robot explode block K, which is block K, DK block, and and then we can show that there always exists a period in the block 2K. So block 2K such that there are two situations. One of the situation of those two situations will happen. So you can see that first situation is that the seeking robot is currently running on the instruction to move, and the second robot just stay in the place. So that the first robot activate early, and the second robot activated later. So that's also means that from this structure we can also identify the situation. That means the first robot which label 1, second robot which label 0. And the opposite way is that if the robot which label 0 activated first, and then second robot which label 1 is activated later. So and then we can guarantee in the block 2K always one of the situation happen, so that you can easily see that when we run one of W2K and another robot will keep stationary. So that's because the W2K contain W2K contain a universal traversal sequence, which guarantee that the whole graph will be solid and will guarantee that the graph will be unique. So this is the idea, intuition of the idea. So, and the second problem is called the treasure hunt problem. The workshop, this is the variation of Rendezvous. One robot is always static. So treasure hunt may be, but the issue is that the treasure one keeping static may be activated after the seeking robot. So because we don't know the when this treasure will be activated. So that's the most challenging part. So in the memoryless model, this is probably equivalent to the existence of strongly universal traversal sequence. So main problem is that this is still open. So we focus on the efficient solution when backtracking are allowed. So that's the sequence called the strongly universal exploration sequence. So which backtracking. So in the literature, there are some major results related to strongly universal exploration sequence and the treasure hunt problem. So Tasama and Zook specify the polynomial time solution for implicit construction in time big of n to power 10th log square n, and they also showed explicit solution which is big of n to power c. So this c is a constant, but it's very large. That's based on the construction of original universal exploration sequence. So, but this is made for strongly universal exploration sequence. So later I improved both version, both implicit version and explicit version dramatically. So, and also the my solution is also almost optimal because this length of the cover time is almost identical as the original universal exploration sequence. So the length of universal exploration sequence, which is almost optimal for this problem, treasure hunt problem. So for the Rendezvous problem, and also improve significantly, so that we should backtracking assumption in backtracking model. So let's look at the some details and the ideas behind this. So now, because we talk about the universal exploration sequence, so we are allowed backtracking, we are allowed to use the knowledge, extra knowledge, because the extra knowledge is that when the robot enter into a new vertex, robot learn the entry to this control vertex. So that's very important because as I mentioned before that the robot may use this information properly and to backtrack to the original position. So universal exploration sequences are similar as universal traversal sequence will actually cover the whole graph. So wonderful, elegant, beautiful work done by Ringo in 2005. This result presented at this result marked as the best paper in best theoretical computer science conference Stock 2005. So Ringo showed that universal exploration sequence can be constructed in polynomial time. So this is a significant step forward on this direction. So now we have this constructed version. So now since we have this universal exploration sequence, then we can use this as a base and combining with smart idea to construct a strongly universal exploration. As mentioned before, this is more powerful than original universal exploration sequence. This one guarantees any contiguous subsequence which proper size which covering time will be also a universal exploration sequence. That's a much powerful property, can be used in many applications. So suppose that we can construct this. Suppose that the UN is a universal exploration sequence for graphs of size n alpha. For some small alpha greater than 0, less than 1. So and suppose that u to the power I is a prefix of u to the power j, so we can easily construct the sequence in this way. So and then we recursively define this strongly universal exploration sequence, and by this Sn. So you can see that now in addition to original universal exploration sequence, we interleave some component between the original element. So for example, in between U1 and U2, we interleaving recursively for strongly universal exploration sequence, which size R1 and followed by 1, 0, and then followed by inverse of SR1 and then followed by 0. So and the size we want to construct between original universal exploration sequence, the component interleaving component is designed or selected as the following way. So we have each index I from the original universal exploration sequence. Now we specify this Ri, because Ri is also related to recursive strongly universal exploration sequence with a smaller size. So Ri defined as a maximal 2i, such as that 2 to power 2. Ri defined as the maximal power for 2j, such that 2 to power 2j will less than I, and loosely speaking, and in such a way that we can give specified value to each interleaving component. And another good intuition is that because now we allow the backtracking, we use the entrance information, and we can show that any sequence SRI followed by 0 inverse of SRI will be returned to the original position. So that's a very good property. So any sequence SR1, any sequence SRI followed by 0 and inverse of Ri will be returned to original position before we run SRI. So that means that that's give a good property, because you can see that if we run, for example, if we run the component SR1 followed by 0 SR1 inverse of SR1, then that means that we return to the original position, but just the opposite direction. Then followed by one extra 0, that means that SR1 0 SR1 inverse of SR1 followed by 0 do nothing. So that means that they will not affect the original universal exploration sequence. So that means that strongly universal exploration sequence also is a universal exploration sequence, but with stronger property. So, and by interleaving different component in between the original universal exploration sequence, for example, we use this rule for interleaving component in original universal exploration sequence. We can get based on careful analysis, we can get the cover time pk. That means the cover time for graph with size k. We can show that this is basically is the figure of UK squared. So, and beware that UK is the best universal exploration sequence. So, and then by another smart interleaving, for example, you can easily see the difference. Now, previously we smartly define Ri. Now we select even more smarter Ri. This case is that we still select the maximal power of 2, such as 2 to the power 3/2j less than I. So based on this rule and based on analysis, we can show that the pk now reduced to UK to power 3/2. And of course, very natural question is that whether we can get a better construction. So for the construction time, for the running time, yes, we can. So we define a new sequence. We call this sequence is a tracer sequence, which is defined as specified by the equations in the red box. And this is the sequence we defined. This is a monotonely decreasing sequence. We can always guarantee there exists item in this sequence less than 1. And based on other smart observation and property, we can show that the cover time now pk is almost reduced to the size of original universal exploration sequence. So that's almost the best you can do. So any better solution for the universal exploration sequence can be also applied to our construction to get a better solution. So yes, so this is for the strongly universal exploration sequence. So there are also a couple of intriguing open problem left. One, of course, we already addressed several times. So the existence of strongly universal traversal sequence. So that's the major open problem for this direction. So, and of course, another very natural open problem is the efficient construction of universal traversal sequence. So, and also exploration sequence as well. So yes. So many thanks. So that's all for today. So.
Okay, Thank you, Professor Keen Jean, for your excellent presentations and discussing some open problems on this topic. And if there is any questions from the audience science, you can ask now.
Yeah, please, yeah.
Any doubt or any questions?
Yeah, any question you can ask. So yeah. Yes, please. Questions, please. Yeah.
Currently, there are questions, I think, but your talk was interesting, and I think some of us will be working on the segment and with you.
Sorry, I cannot hear you clearly. So can you repeat your question?
Questions, but your stimulating and
Yeah,
will be future.
it seems I really cannot hear you clearly. Yeah. Can you speak slowly? Yeah.
Sir,
I think, sir, there is a network issue in this side, so it is not audible clearly.
so,
Yeah.
we thank the show, Dr. Mohan, show, and before closing,
Yeah, the quality of sound getting much worse.
So, Professor Jing, sir, there is no questions from these sides, and I think this is the end of this sessions. And there is a network issue, so that's why it's been not audible properly from the university side. And this is the certificate, and this from the organizer side to you, Professor Jin.
Oh, really appreciate it. It's my great pleasure. So really appreciate it. Much appreciated. Yeah.
yes, the subject is that
Yeah.
research achievements.
So I really cannot hear you clearly. Maybe you can send me by email. You can send your question by email. Yeah.
Definitely send it to everyone. So,
Yeah.
thank you, Professor.
Professor Jin, this is the Research Excellence Award from this conference and to offer to you. And this will be obviously sent to you through email. Can you see
Yeah.
the screen, Professor Jin?
Really appreciate it. Really appreciate it. Yeah.
Okay. Thank you, mate.
Okay, sir. This is the
Yeah.
end of
Really,
this.
yeah, you can always. Yeah. If you have any further question, you can send me by email. Yeah. Always welcome.
Surely,
So
surely.
because the sound quality sounds a little bit unstable. So